Hey, so this is the fourth installment of Shor's algorithm series. We are going to talk about elliptic curve cryptography because elliptic curve is one of those encryption that is used predominantly um, in we use it in our daily lives, like for example when we use our phone and then send messages that are encrypted. These are using this kind of technology. So elliptic curve cryptography versus RSA. So RSA is based on the hardness of factoring a very big number, whereas elliptic curve cryptography is based on some geometric, um, uh, uh, based on the hardness of what is known as the solving the discrete logarithm. So in elliptic curve cryptography, okay, before I go there, this is very, the reason why we have this as an option is because this one, according to research, you only need a few keys in order to have the same or equivalent power as the RSA. So, for example, 256 bits of key in elliptic curve cryptography, or ECC, is equivalent to 3072 bits or 3072 bits of RSA. And so, because of that, it doesn't need too much power or computing power to be able to encrypt or decrypt using elliptic curve cryptography. So that's why this one is used in like our mobile phones and IoT devices. So low power devices that need encryption. This is the algorithm that is used. Yeah. So, and the thing about ECC is um, um, which is the same as the RSA, that this has a mathematical structure. And because this has a mathematical structure, there is a formula. If you know if you know the private key, so you know how to reverse the encryption. And because of that, that's the reason why it's amenable to um, uh, being attacked by a quantum computer. Okay, so so in this particular session, we will just focus first on what is elliptic curve cryptography. Yeah, this is an interesting topic in itself. Okay, so let's start with where am I? So there is this equation called the elliptic curve, and it is defined by this formula here, which is y squared is equal to x cubed plus ax plus b. And depending on the values of a and b, you can have two different, so it looks like this. So in the elliptic curve, what we are trying to get is, so imagine there is a, so this elliptic curve covers all of the, so it extends to infinity. So here I'm just showing a portion of that. So which means that if you have any line that intersects the curve, so it can intersect this curve in three ways. So one is intersecting at 3 points. The other is intersecting it at 2 points only. And the last one is intersecting it at 1 point. Okay, so it's a tangent to the point. Tangent to the curve at that point. Okay, so so the good thing about this elliptic curve is we can define a mathematical structure. So just like in mathematics, you know, when we think of when we were young, especially when I was young, I thought mathematics was all about adding numbers or multiplying or dividing, and you know, I'm not really good at that. So that's why initially I hated mathematics. But then, because turns out that mathematics is about abstraction, and you don't need to add or multiply numbers, but you can represent them as letters, you know. So that got me interested, because at least my you know, my what you call this, my weakness, you know, in multiplying, dividing, you know, adding numbers, you know, is not that would not be that would not be counted. I mean, it's I can still do mathematics even if I multiply poorly, no? So the same goes here. You can define a mathematical structure. Okay, so you can define addition. Okay, it's an addition of points. So when you add points, so I'm getting ahead of myself. So when you have 2 points in an elliptic curve, you can define, you can derive a third point by adding them. Okay, so you add 2 points and you get a third point. So in here, first, the first thing that we want to define is the negative of a point. So it says here that if you have a point Q, then the negative of the point Q is the point P, which is the mirror image of the a point Q is the negative of a point P if point Q is the mirror image. So as you can see here, you have a P, and the negative of P is the mirror image. So if you have a line that intersects the curve perpendicularly, the point that you get here is the negative of P. So now we define the negative of a point. Okay, so that's the beginning of our algebra. Okay, so from the relation which we defined above, we can now define the number, or the point 0 or O, or the point at infinity. Okay, so we define it as P added to its negative. So P plus the negative of P gives you the point O. Okay, so in mathematics, we usually do this, no? So in order to make our algebra complete, okay, so for example, this one infinity, okay, in order to make our algebra complete on a set of objects, we have to add that thing which completes it. So in this particular case, we have to add a point at infinity, which we define to be like this, in order for our algebra to make sense. Okay, so now we have we have defined the negative of a point, and now we have defined the point 0, or the point at infinity. So when you add P to its negative, it will give you 0. Because 0 here is not the typical 0 that we know in the real numbers, but it's a point, the point at infinity. Okay, so now suppose we have a line that intersects E at so E here is the elliptic curve. Okay, so we have a line that intersects the elliptic curve at points P, Q, R. Okay, now we define the sum. okay, the sum of P plus Q and R to be equal to the point infinity, 0. Okay, so this is definition. Yeah, so as in mathematics, you don't need to prove definition. Okay, so it's a given. It's like an axiom. So we define this P plus Q plus R to be 0. And from this definition, we can now see that P plus Q is equal to negative R. Okay, so that's this one is derived. Okay, okay, so we have P plus Q equals minus R. Now, how do we actually add 2 points given the coordinates? Okay, so if we are given the x and y coordinates of the 2 points, since so we have 2 points and the 2 points is connected by a line, right? And the equation of a line in general in a 2-dimensional coordinate system is y equals mx plus c, okay, where m is the slope of the line and c is a constant. Okay, so if we have a line and we want to compute for the intersection of this line with the elliptic curve at points P, Q, and R, then you can solve it. Well, you can, for example, use Mathematica to solve this, and it will give you this these coordinates. Okay, x1, x2, and x3. Okay, where A and B here are these expressions. Okay, so A and B. Okay, but the good thing is we don't really need to know what A and B is, because that's not, turns out that we don't, for our purposes, we don't need to know that. Why? Because, so if you add, for example, this one here, if you add them, x1, x2, x3, okay, you will actually get the slope squared. So which means that you can, since x1 and x2 are given, then you can get the third point. Okay, so when you add 2 points to get the third point, so the 2 points, you know the x1 and x2 coordinates at that point. So to get the third point, this is the formula. Okay, m squared minus x1 minus x2. And to get the y coordinate of the third point, you just use the formula of the slope. Okay, so the formula of the slope is y3 minus y1 over x3 minus x1. Okay, so this was a familiar equation in high school. So this is the slope, and then you get the third point. Okay, so this is the formula. So which means we already have a way to compute the third point. Okay, so given 2 points. Now, if it turns out that the point is tangent to the curve, okay, at point P, you can compute for the slope. So let me go back one page. So this is how we compute the slope, right? If it's not tangent, no? But if it's tangent to the curve, then you can use your differential calculus to derive the formula. And so dy dx here, which is the slope, is just equal to the derivative of the elliptic curve. Okay, is equal to 3x squared plus a over 2y. Okay, and the good thing is you don't need to even remember that, because we are going to program it. So this one is a is a code. Okay, so yeah, this is not Python code. This is actually a code using R. Yeah, so R is one of the two languages being used in data science. So one of them is Python and the other is R. So I'm very familiar with R because I have been using it since for already 22 years. Okay? So R. So I'm very familiar, but I'm going to at the moment trying to convert this to, well, actually I already converted this to Python, but I haven't updated the slides. Okay, but I can show you the code. Okay, so let's take a look at the code. Okay, can you still hear me now?
Yes, we are able to hear you, sir.
Okay, so let's take a look at the code. Okay, yeah, so this one is a Python Python code for the slope. Okay, so if you take a look at this one here, this is very similar to this one. Okay, slope. And I also define here the when you add two points. Okay, okay, so going back to the presentation, so so now that we have seen how to add 2 points, okay, so given two points P and Q, okay, so P is x1 y1 and Q is x2 y2, then the third point, okay, so take a look at this. Okay, the third point is x3 comma negative y3. Okay, so if you remember, we had a drawing earlier for which the third point is the what you call this, the negative of let's go back to the drawing. Okay, so if you add P and Q, then you get this. Okay, so minus R. That's why we have a negative. Okay, that's why we have a negative. Okay, that's why you have negative y3. Okay, so and you have, so this is just a summary. We have x3 and y3 given by these formulas, and m is given by these two formulas. And so with that, it's easy now to just create a program, yeah, to make our computation easy. So it says here, important, yeah, take note, okay, that the R, which is equal to x3 negative y3, the value of y3 should be the negative, the computed value. Okay, so that's what I explained earlier. Now, so let's an example here. Let the elliptic curve be this one. So x cubed minus 3x plus 3, and then you have points negative 2, 1, and 0. Okay, so if you are very familiar with this 1.732 is actually the square root of 3. So so lie on the curve. So the third point can be computed as follows. Okay, so you just plug into the formula and to get this. Okay, so let's do that. Okay, okay, I found out that it's easier to learn if the teacher is not too fast. Okay, that's why let's have some coding in order to make it slower. So we have the formula of a slope. So so first thing is to import the ECC. So the ECC is the file name. Okay, this one, the file name of this is okay. So this one is an ECC. Okay, and it's in the same directory. Okay, so this one is a Python terminal. Okay, so now in the ECC we can compute for the slope. Okay, so there's a definition here. The slope is you just input the value of x1 of the coordinates. Okay, x1, y1, x2, y2. So if we do that, we have ECC that slope. What's x1? Okay, minus 2 and 1, and then 0, and then 1.732051. Okay, So it gives us this one here, okay, 0.366. Now, so we just use the formula in order to get x3, okay? x3 is equal to, okay, so before I do that, I have to assign this to m, okay? So which means x3 is equal to x squared, okay? So power of m raised to the 2 minus x1 minus x2. Okay, so x3 equals 2.133. And finally, we have y3 is equal to m times x3 minus x1 plus y1. Okay, so y3 is, oh, it happened. x3 minus x1 plus y1. M is 0.366. x3 equals 21. x1. Oh, where is x1? Ah, okay, sorry. I did not define x1. Okay, x1 is equal to minus 2. Okay, so if I do that again, we have y3. Sorry, guys, x1. Okay, let me just do this. So, okay, m times x3 minus x1 plus, oh, okay, I did not define one. Okay, y1 equals 1. Okay. Okay, 2.5. Okay, so this one now matches. Okay. Okay, so that's how you compute for the third point. Okay, but so therefore this is if you graph it, okay, so this is your point P1 and your point Q, and this is what you get for the third point, but this is not what we are after. What we're after is actually this one here. Okay, so the negative of this point, okay, so which is the mirror image. Okay, now now let's have an example. If P1, if P and Q are the same point, what would happen? So if we have P and Q, so we have x1 is equal to minus 2. Okay, sorry. x1 is equal to y1 is equal to minus 2. x2 is equal to y2 is equal to 1. Then we have ECC that slope will give you of x1, y1, x2, y2. Okay. Okay. x1, x1. sorry, guys. x1, x2, sorry, x2, and y1 is equal to y2 is equal to 1. Okay. Yeah, 4.5. Okay. And then, yeah, you just substitute, and then you get the point. Okay, so it's just it's very easy to do that once you have programmed it. And so this one here, as you can see, this one is tangent. Okay, so it's tangent to the point at this at point P. So P and Q are the same, and the third point is here, and it's quite you know, it's 25. It's you have a smaller graph because the range is quite long. Okay, so this is just the add function. Okay, Now, so now that we have identified operations into our set of points called the elliptic curve, it turns out that we can define a group structure. So this set of points and the mathematical operation that is associated with them, it turns out that it defines a group, okay? Because if you add P and Q plus R, so it's associative, no? You can get the same result by adding Q and R first before adding P, okay? And every element has an inverse, okay? And it contains the identity element, which is 0, or the point at infinity. Okay, so P plus 0 equals P, which makes 0. Let's just call this O. O, the identity element. And also it is closed. Okay, so which means that for any PQ and the result of adding them, it is a point also in the elliptic curve. Okay, so that's the meaning of a closed operation. So sometimes, especially in physics, if you define a new algebra and it turns out that your algebra is not closed, then it is highly suspect. Okay, so it's possible that you cannot trust whatever prediction that that theory has. Okay, so this is very important. The property of being close. Okay. Now, so the addition formula turns out also works for modular operation. Okay, so so if you add 2 points and to get the third point, then so we now add modular arithmetic here. So if you get the third point, you just get the modulo of some number P. Okay, so since you let P be a prime number, then given 2 points P and Q, the third point can be computed as follows. Okay, so just do this operation and then get the modulo P. Okay, and the same goes for Y. Okay, where M is defined to be this one here. Okay, so that's modulo. And there's also a code here to get the slope modulo. Okay, so what is important here is that there is this mod div. Okay, so if we go back here, in order to compute for M, okay, so you have numbers, right? So y1 minus y2. Okay, so if you have numbers y1 minus y2 divided by x1 minus x2, the way to compute for the slope modulo P is first you get the inverse modulo of this number. Okay, so 1 over x1 minus x2, you get the inverse modulo of that. And after getting the inverse modulo, you multiply it to this one, mod P, to get the to get M. Okay, so what you don't do is you compute this and then you divide this by this one before getting the modulo. Okay, so that's not correct. Okay, so that's why we have a mod div. Okay, so which is to get the inverse modulo. This one is the mod div. So if you remember, you see, in our previous discussion, you know, if you have a number, let us say Q is equal to some number S times M plus R. Okay. So just let me just this is the okay. Sorry, I have to. Hey, welcome. Yeah, yeah, thanks for attending, Kevin. We are already near the middle, but that's okay. I have the slides. So I was just I was trying to explain the concept of modulo. So if you have a number and you want to divide it by a certain number m, yeah, if you want to divide it a certain number m, then you get a remainder r. Okay, so r can be if there's a remainder, that's r. So when you say when you say q is equal to r modulo m, that's the this is what this means. Okay, so let me just copy this. Okay, because this one is it's a familiar concept. Okay, and it might not be familiar. Okay, so when you say q is equal to r modulo m, this is what this means. There is a number s such that if you multiply it to m and you add r, you get q. Okay, so that's the meaning of modulo. Now, yeah, so that's the meaning of modulo. Now, let's go back to this. Yeah, let's go back here. So, so in terms of the when you divide a number, okay. So when you get the modulo of sorry, what's this? So as I was discussing earlier, if you want to compute for this one, what you do is first get this get the result of 1 over x1 minus x2 modulo p, and the result of that you multiply it with this one here. So that's the proper way. Okay, so usually you will what's not correct is if you get this value divided by this value and get the modulo. Okay, that's not how it works. Okay, so yeah. Okay, so suppose we have a number. So suppose we have a prime number p equal to 71. Okay, and then we have 2 points p and q. How do we compute for the third point? Okay, so for the benefit of sorry, I'm not able to. It's okay. Okay. Yeah. You can you can always what you call this speak. You can always disturb me if you have something to say. Yeah. Okay, so let's take a look at this. So we have a point P. Sorry, we have a prime number P equal to 71. Sorry, for the benefit of Kevin, let me just. So we are trying to compute the third point of an elliptic curve. So let me just show the geometry of that one here. So this is what we are trying to compute, Kevin. So we have here, so if you have P and Q, and you want to, this one is P and Q, and you want to get the third point. Okay, the third point is defined to be the mirror image of the point R that is collinear with this line here. Okay, so you have a line that intersects your elliptic curve in 3 points. Okay, so by definition, if P plus Q plus R is equal to 0, okay, so where 0 here is what is known as the point at infinity. Okay, now so in other words, this is a point there in infinity. Okay, so if you add this, if you add this 3, so this is a mathematical definition. Okay, so we are actually creating mathematics or algebra over the set of points in elliptic curve. Okay, so this is an algebra of points, and so you define P, Q, and R to be equal to the point infinity. Therefore, if you define that, then you have P plus Q is equal to minus R, and the minus R is just by definition this one here, the negative. The negative of this is the mirror image of this point. The mirror image of this point across the vertical line, which is this one here, imaginary vertical line. Okay, so let's go back.
Hello. Can I ask?
Yeah.
So this is an elliptic curve.
Yes.
I cannot visualize, but what is this this geometry? What's the equation of the?
Oh yeah. That's a very good question. So
Because I was trying to imagine a conic, the usual elliptic shape. So what is that section?
elliptic curve has nothing to do with ellipses. Okay, so this is the equation of this of the.
Oh, I see. Okay.
Yeah. So where A and B are real numbers.
Okay. Thank you. Thank you.
Yeah. And for our so I have examples here. I fix an elliptic curve, and the equation of that elliptic curve is let's see. I think this one here. Okay. Yeah, so the equation of the elliptic curve is, what's it? I mean, it's okay to distract me. We were just talking about. Yeah, this one here. This one is the equation of the elliptic curve. Okay, so we have to agree on the equation in advance. Okay, so that's x cubed minus 3x plus 3. Okay. Now, so where was I? So I was talking about having the set of points in the elliptic curve plus the operation called plus, okay, which we define, turns out to be a group because it satisfies all of this, satisfies associativity, okay, elements as an inverse, and then it contains the identity element, and also it is closed. Okay, so group theory. So this one is the beginnings of group theory. Group theory proved to be very useful, okay, in physics, especially in quantum mechanics, and also when you study For example, particle physics, the quarks. You know, if you've heard about the you know, the God particle, the bosons. You know, there's a lot of the quarks have different colors. So it turns out all of that were predicted by the theory, and which uses the group theory. And also the group theory was was also the mathematics that was used by Évariste Galois to prove that what did he prove, that the quintic equation doesn't have an analytical solution. So which means you cannot express the solution as numbers, as radical numbers. Okay. So it's very powerful, and it's also the one that's used by Emmy Noether. So she's a very you know, she's a lady, and she's a mathematician, and she proved some theorems using group theory that which says that a dynamical system that has a conserved that is symmetric has a conserved quantity. So, for example, the momentum is conserved, something like that. Okay, so I digress. So let me. It's a powerful theory. So so where was I now? So let me just see. Okay, yeah. So so let me go back. So now so we have a prime number p, okay, which is the base, okay, of our modulo, and 2 points in the elliptic curve. Okay, so 2 points, 0, 28, and -2 and 1. How do we compute for the third point? Okay, so to compute for the third point, yeah, so you just use the formula. So the formula, it's actually in here. No, this one here. So this is the one that I'm going to use. Okay, so first we compute the slope. Okay, so the slope is letter M. Okay, letter M. And then after we compute the slope, we can then compute x3 and y3, which is the third point. Okay, so mod slope. Okay. So if we have just okay, so we have x1 is equal to 0, and then y1 is equal to 28, and then we have x2 is equal to -2. Oh, sorry, x -2, and y2 is equal to 1. Then we have ECC, the mod slope, x1, y1, x2, y2, okay, gives us 49. Okay. Okay. And then it's just a matter of substituting the values to get x3. So we'll just compute x3. So x3 is equal to tau of m squared minus x1 minus x2. Okay, and then we get the modulo. Okay, 71. Okay, we get, oh sorry, hold on, something wrong here. M2 tau M2. So what's my x1? 0, x2, mod 7. Oh, okay, sorry.
Maybe the M, you have to write 49 instead.
Okay. Okay, Pau, M, right? M2. Okay. What happened to my M? Oh, sorry. Yeah,
Yeah, maybe you have to
You're right.
maybe it's not returning as M equals 49.
You're right.
Yeah.
Okay. I always get this error because I always fail to assign values
Yes.
to variables.
Every programmer experiences that. I
Yeah.
understand.
So X3. So we get no X3. Okay. And then Y3 is the same thing. So what does that mean? Now that you have your X3 and Y3, then the third point is nothing but 60 and negative 57. Okay. So you have to remember that the third point is the mirror image. Okay. So if you have a point 60 comma 57, then the mirror image is 60 comma negative 57. Okay. Now it turns out that minus 57 percent 71 is equal to 14. Okay, so that's why we have 60 and 14 here. Okay. Now, okay, so now let's define multiplication of points. Okay, so we already defined addition, but multiplication of a point B is nothing but adding. So if you multiply a number n to the point B, this is nothing but adding B n times. Okay, so that's the definition. So example, so if we have B is equal to 0 and 28, 0, 28, then using the formulas, so using, yeah, so we can actually program that one here. Let me show you this one here. So the definition of multiplication. So mod mul. Okay, so if you have a B, if you have a point B, so what you do is just add it n times. Okay, so add it n times using this function, and then you'll get your result. Okay, so if we do that, okay, so we have the B is equal to 0 and 28. Okay, then mod ECC that mod mul B comma 3. Okay, so that should give us 3763. Okay, that's the result of multiplying this by a number n. Okay. Okay, I think we now have all the ingredients that we need in order to define the elliptic curve cryptography. Okay, so let's take a look at this. Alice and Bob want to exchange information, okay, using elliptic curve cryptography. So the proverbial Alice and Bob. So these are the main characters when it comes to cryptography. And there's another one called Eve, who is the eavesdropper. But Eve will not figure in this session. Okay, so Alice and Bob, they want to exchange information. So they had to agree on an elliptic curve equation and a base point B. So Alice and Bob, they choose a random number, okay, which is between 1 and 71, and it has to be prime. Okay, so we have EA and EB. So let's call this EA and EB. So this is the number that Alice picked. Okay, So that's why we have a subscript here, A. And for Bob, this is the number that Bob chose, okay, between 1 and 71, okay? Now, this EA and EB, these are secret, okay? So no one should know about this number except Alice for EA and Bob for EB, okay? Otherwise, someone will, if they know this number, then it will be very easy for them to decrypt communication between Alice and Bob. Okay, now you have a private key. Now let's derive a public key. So the public key is something which we, attach to our email. We publish for the whole world to see, so that anyone who wants to message, for example, Alice or Bob, they can just use the public key to encrypt the information. Okay, so the public key in this case is for Alice is EA multiplied by the base point B. Okay, so remember, we already know how to multiply points, right? Okay, just want to refresh your memories. This is how we do it, okay? And for Bob, this is the public key, okay? So Bob will get his number, multiply the base point with the number, and publish it, okay? Because he knows that no one will be able to, it's very hard. Let's just say it's so hard to derive EB, okay, E of B or E sub B, given this information, okay? So given this information, it's so hard to derive this, okay? So if Alice wants to send a message encoded in the point, so you have a message, okay? A message is a number, no? Everything should be translated to a number, and that number, you get the corresponding point in the elliptic curve, okay? So meron kang number, get the corresponding point in the elliptic curve, okay? And call it point P. So once you get P, this is the information you want to send to Bob, okay? So you want to send this information, but you want to encrypt it. So how would you do that? How would Alice do that? So Alice, what she does is get the public key of Bob, which is this one here, okay? So this one is a point, right? This one is a point in the elliptic curve. And then she adds to it, she multiplies it with her private key, okay? So this is the result, okay? Bob's public key multiplied by Eve's private key is this thing here, this expression, okay? And we know how to do that, right? We know how to multiply numbers to points. And once she gets this number, or once she gets this point, all she had to do is to add it to the message P. And we also know how to add 2 points, right? So, which means we already know how to encrypt using elliptic curve. So the result of this is this encrypted message, okay? Or we call it the cipher text. And the, what's this? This is the, okay, I made a mistake. So, yeah, that's right. This is the public key of Alice, okay? So Alice will send her public key as well as the message, which is encrypted message, okay, to Bob. And anyone can actually read it, okay? But only Bob can decrypt. So that's the whole point about encryption. Okay, so that is how to encrypt using elliptic curve, okay? So let's apply that. So before we do that, so Bob receives the message, okay? So nakuha na ni Bob yung message, no? And what he does is he has his private key, E of B, or E sub B. And since this one was sent by Alice, okay, remember this one was sent by Alice, this one here. So what Bob needs to do is multiply Alice's public key with his private key to get this expression, okay? And once you get this expression, you just add it to the message. You subtract it to the message, okay? This is the message. When you subtract it, all you get is the original message, P, okay? So that's encryption and decryption using elliptic curve cryptography, okay? Okay, so now assume, this is an example. So assume that Alice and Bob agree on the equation and the base point, okay, 1, 70. And the modulus P is equal to 71. So suppose private key of Alice is 5 and Bob's private key is 7. And then Alice will publish her public key as this one here and Bob as this one here. Okay, so let's do that. Okay, so let's say that Alice here is equal to so Alice's private key is 5, right? Okay. Then,
Can I ask a question?
yeah.
So is the key only limited to real numbers?
Yes, because the prime numbers, integers.
Oh,
Because we are
integer.
dealing here with modular arithmetic.
Oh, okay. Thank you.
Yeah. Okay, so Alice and Bob, and then let's define Alice B equal to ECC dot mod mul. So we multiply. Okay, let me define B first. Okay? B is equal to 1, 70. Okay, so we have Alice equal to multiply B by the private key of Alice to get the public key of Alice. Okay, so this is the public key of Alice, which is 4659. So in the same way, let's compute for the public key of Bob. Okay, Bob B is equal to ECC mod mult B and Bob. Okay, so Bob B is 7054. Okay, so these two pairs of numbers are the public keys of Alice and Bob. Okay, so they attach this to their emails, publish this to their LinkedIn. So anyone who wants to message them will be able to do so in a secure manner. Okay. Now, so okay. Okay, so now Alice wants to send Bob a message encoded in the point P. Okay, so P here is the message that we want to send. Okay, to send to Bob. Okay, so normally it's like this, huh? So you have so you might be wondering, where's the message? Why is it at 1754? Where's the actual message? Okay, so the actual message is, for example, it's a character which is mapped to the number 17. Okay, so once you get number 17, you just get the corresponding number, which is 54. So inside, you just get the corresponding number, the corresponding y coordinate in order for this point to be inside the elliptic curve. Okay, so how do you get 54? Since you have the equation of the elliptic curve, which is equal to y cubed is equal to x cubed minus 3x plus 3. So you can already compute for the y coordinate. Okay, so this is P. Okay, this is the message we want to this is the message we want to send to Bob. Okay, so how will Alice do it? So first, Alice will multiply Bob's public key with her private key to get this. Okay, and then she will add this to the message. Okay, to get this one here. And then this is the one which she will send to Bob. Okay, so let's do that. Okay, so we have a message 1754. So first we're going to compute for EA multiplied by Bob's public key. Okay, so that's Alice. So that's Alice, right? So Bob's public key. Bob's public key is Bob B, right? Okay. So in order to compute for EA, okay, so let's just call this Alice Bob, okay, is equal to ECC dot mod Bob P, okay, this one here, and multiply it with the Alice 5, okay, so multiplied by Alice, okay, so Alice Bob, okay, so you get this 4951, and then you add it to the message. So the message is P, so we have ECC that mod add x1 is 17, okay, y1 is 54, and then the Alice Bob is 4159, okay. So you get this 2539. So this is the one that you sent to Bob, okay. So how does Bob decrypt this? Okay, so Bob will decrypt that using this. So what Bob will do is he will guys, can you read this, or do I need to maximize?
Yeah, we can already read it. It's okay.
That's good. So yeah, it's happening to my laptop. Okay. Okay, so Bob receives 2539 as the encrypted text. So the first thing he does is to multiply his private key with the public key of Alice. So let's call that Bob Alice is equal to ECC that mod Alice private key, public key, comma, Bob. Okay. So we have Bob Alice. Okay. Which is 4159. Okay. And then we are going to subtract this to the encrypted image. Okay. So subtraction, how do we subtract? So what we do is use the addition formula, right? So using the mirror image of the point. So so to do that, we have mod add, sorry, ECC that mod add. We have our point, our encrypted text, which is 2539. Okay, so 2539, and then we subtract this to this one here. Okay, 4159. But since we are using the since this subtraction, we are going to use the mirror image. Okay, so this one. So we have 41, comma, minus 59. Okay. So 1754. So as you can see, guys, this is the message that Alice sent. Okay, so this is the message that Alice sent. Okay, 1754. Okay, so that's it. So that's the elliptic curve cryptography. I think that's the end of my Yeah, so that's the end, guys. Okay, I am going to give you later. Thanks for attending. An assignment. Okay. You may or may not do it, but I encourage you to do it, especially Kevin here. Okay, so if Kevin will do the assignment, I'm going to give you a T-shirt. Okay, with the logo One Quantum Philippines. Okay, let's say. So Asher already did that before, so he did not do the assignment. But yeah, so I will send the assignment later. But this is the end of the elliptic curve lecture. Okay, so in summary, elliptic curve is a public key infrastructure encryption encryption algorithm. Okay, which is and there is another one called RSA. Okay, which stands for Rivest Shamir Adelman. Okay, so these are the those are the inventors. So RSA is another encryption based on the hardness of factoring a very huge number. Okay, a very huge composite number. So that's the RSA. So this one's elliptic curve. And why is elliptic curve very important? It's because we are currently using elliptic curve cryptography in many of our encryption. For example, when you use WhatsApp, okay, and it says there end-to-end encryption, that one is using elliptic curve cryptography. So when you want to digitally sign your, for example, digital document using, you can use elliptic curve for that. Okay, elliptic curve is also being used in the blockchain. Okay, or the Bitcoin. Okay, so and the thing about elliptic curve is that with only a few bits, it has it's equivalent in power to a RSA with many bits. So for example, there's research that 256 bits of elliptic curve has the same encryption power as the 3072 bits RSA. Okay, and because of that, it only needs little CPU and memory to be able to encrypt and decrypt using elliptic curve cryptography. And because of that, this elliptic curve cryptography is very useful for low power devices. Okay, so cell phone, tablets, IoT devices that encrypt data are using elliptic curve. So, and the reason why we are talking about elliptic curve is because it turns out that in the same way as RSA, these two powerful crypto systems have a very nice mathematical structure. Okay, so these are both of them are actually instances of what is known as the hidden subgroup problem. Okay, so and the hidden subgroup problem is the kind of problem that can be solved easily by Shor's algorithm. Okay, so as you can see, the very different at at the surface, both of them are very different. So one is using factoring of large numbers, and the other one is using geometry. But from an abstract mathematical point of view, they are the same. And that's the reason why Shor's algorithm can decrypt them. Okay, so that's, do you have any questions?
Hello. So just to clarify, other than each other's public key, we also need to know the equation of the
Yes.
elliptical curve. So is it built in within the program, let's say, between the communication media, or
Yes,
do I
yes.
also send that information?
No, the elliptic curve, the elliptic curve itself is standard. So there are standard elliptic curves, and also base points. So the only thing that you need to actually generate is the private key. So once you have once you have your private key, then it's very easy to generate the public key and then publish it. Yeah.
Thank you. Thank you.
Any more questions?
I got one question. I'd just like to know, like, how does the size of the elliptic curve determine its difficulty? Like the difficulty for breaking or cracking the message.
Yeah, that's a very that's a very very good question, Asher. So so honestly, I don't know how, but probably there are some references that we can read on how does it mathematically, from mathematical point of view, how do you derive the strength of why can you say that a 256-bit elliptic curve has the same power as a 72-bit RSA?
Okay, sir, got it. I think that would
That's an
probably
assignment
be
next
one of
week.
my assignment. Yeah. Thank you, sir.
Yes. Okay, so if there are no more questions, in our next, so this is the fourth of a series, right? So in the succeeding series, which follows this, we are going to show theoretically how a quantum computer can decrypt an elliptic curve cryptography using Shor's algorithm. And the next session after that, we are going to derive the circuit, the circuit of the quantum Fourier transform, which is a big part of the algorithm of Shor. So yeah, so we use the mathematics in order to derive the circuit. Okay, and then lastly, in the 7th lecture, we are then going to tie all of these up together by giving an example of a number that of RSA encryption, and we are going to decrypt that using Shor's algorithm, which is implemented as a circuit.